Hey, welcome to another three-dimensional space example. So in this problem, we are going to be looking at the equilibrium of a particular particle in space. And we have this diagram drawn here, so it looks a little confusing, so I'll try to explain it the best I can. Basically, we have this little weight here. That weighs 376 newtons, and it's supported by a single cable that starts from B, loops at A, and then ends at C. So this is one single cable. And the supports B and C are within the plane XZ. So if you can sort of imagine the plane that this x-axis and the z-axis make, so this plane right here, points B and C are within that plane. In other words, their y-coordinate is 0. And at point A, where the bucket is tied to the cable, we have two additional forces, P and Q, that are keeping this entire system in equilibrium. So P and Q are actually pretty special in the sense that P only has an x component, P, in the I direction, in the x component. So this P force is parallel to this x-axis and it's in the positive direction. And in the same sense, we have this force Q that only has one component, in this case in the k direction or the z direction. So this force vector right here is parallel to the positive z-axis. Now each one of these points A, B, and C have certain coordinates. So point A is located at an x of 0, a y of negative 400, and a z of 0. So if we started here at the origin, you can see that x is 0, and then we go down negative 400, and then z is also 0. So that's where point A is located. And in that same sense, we have points B and C, which have different coordinates. So anyway, that is sort of the diagram. And the question is asking, what is P and Q? What are the components P and Q to keep this entire system in equilibrium? So what does it mean for a system to be in equilibrium? Well, if you remember from 2D examples, a particle in a 2D space was in equilibrium when the sum of all the forces in the x direction was equal to 0 and the sum of all the forces in the y direction were equal to 0. Now 3D is not much different. In this case, we just have one more component to worry about, one more direction, and that of course is the z direction. So in this case, for systems in equilibrium in 3 dimensions, the sum of the forces in the z direction must also equal 0. So how can we use this knowledge of equilibrium to figure out what P and Q are? Well, if we know that P and Q are keeping this entire system in equilibrium, then we would need to know the x component, the y component, and the z components of all of the forces that are acting at point A, right? That is the particle that is in equilibrium. We have this little weight, this little bucket. There's a Q force, a P force, and then also these two tension forces, all acting at point A. So essentially what we would need to do is we would need to look at each one of these forces, P, Q, the two tensions, as well as the weight, 376 newtons, and we would need to sum all their x components and set that equal to 0, and then set all the y components equal to 0 and all the z components equal to 0. And we can use those equations to figure out what P and Q are. Okay, so for any of these problems, the good place to always start is to look at your particle and try to come up with a free body diagram of that particle. So for the free body diagram, I'm actually going to just use this same diagram here, where we have this Q force acting in the positive z direction, we have this P force acting in the positive x direction, and then we have these two cables, or it's the same cable, but we have two different tension forces along those cables. And those tension forces are going to be the same because of this statement right here. So here I'm going to draw a tension force that's acting along line AC, and I'll call that TAC, the tension of line AC. And in that same sense, I'm also going to draw a force vector right here, and I'll label this TAB, and that's the tension force going from point A to point B. Now, because of this statement, we know that the magnitude of TAB is going to equal the magnitude of TAC. And so I can simply call the magnitudes for both of these tension forces just T, just for simplicity. Now, continuing on with our free body diagram, there's one more force that we need to introduce, and that is this W force, which is acting downward. So the weight is 376 newtons, so our force vector for W is going to act downwards. And I'll call this W, and this will be equal to 376 newtons. Now, this is important because, again, we need to know the X, the Y, and the Z components for all of these forces to use this equation to figure out what P and Q are. Now, you'll notice that P only has a component acting in the X direction, Q has a component acting in the Z direction, and then W is the only force going straight down in the Y direction. These two tension forces, TAC and TAB, they have components in all different directions. They have an X component, a Y component, and a Z component. And that's going to be important when we try to figure out what those components are. Okay, so because P, W, and Q are pretty simple and straightforward, let's focus our efforts on TAC and TAB. Now, in order to get these components for these three equations, we need to represent each one of these two forces, each one of the two tension forces, in terms of the direction that their line of action is making. So remember, as a general equation up here, I can write that our forces in 3D space are equal to the scalar component of that force times this thing called lambda, which is the unit vector along the line of action of F. So in this case, because we have two different forces in 3D, each one of these forces are going to have their own lambda. So a good place to start is to try to figure out the lambda for both TAC and TAB. So I can start doing that down here. Now I can pick either TAB or TAC first. It doesn't really matter. Let's just go with TAB first. And let's try to figure out what our lambda value is. Now remember, our lambda value is based on the orientation that this tension force makes in three-dimensional space. Now, in order to figure out what lambda is, we need to pick any 2 points along the line of action of that tension force, and that will give us our d values, our dx, dy, and dz. Now, if I drew another vector starting from point A, because that's where the tension force is acting, and ending at point B, then our lambda value would be that vector, AB, over the magnitude of that vector. Now, what is this vector AB? Well, we don't really care what that vector is. We just care that we know how to find its component. So this vector AB has a component dx in the I direction, and then it has a component dy in the j direction, and then a component dz in the k direction. Now, these components are distances from the starting point of that vector, or the tail, to the tip of that vector, which is the ending point. And dx, dy, and dz are simply the distances in the x direction, the y direction, and the z direction. And signs do matter. So because the vector is this way, we know that our starting point is A and our ending point is B. So in order to find, let's say for an example, dx, we need to take the x-coordinate of the ending point minus the x-coordinate of the starting point. Now, all of this is going to be over just d, which is going to be the length of that vector AB. So again, it's just the distance, the absolute distance from point A to point B. Okay, so let's try to break this down even more and try to figure out dx, dy, and dz. So for dx, we know that that is the distance in the x direction from the starting point to the ending point. So if we're looking at point A and point B, the starting is point A, and the x-coordinate of point A is this 0 value. Now, the x-coordinate of this point B is negative 130. And remember, dx is our ending minus our start. So our ending is negative 130, and our start is 0. So dx would simply be negative 130 minus 0 in the I direction. Okay, what about for dy? dy, again, same thing, it's the direction in the y-axis. So if we look at our 2 points A and B, B, the ending point, has a 0 coordinate for y, and for A, it has a value of negative 400. So our y component is going to be, again, end minus start. So end was point B, which was 0, and then minus our starting value, which was negative 400, and that is in the j direction. Okay, awesome. How about lastly dz? Again, that's just the ending z minus the ending a. So that is going to be 160 minus 0 in the z direction. And this is all going to be over d. Now, we'll get to d in a second, but let's simplify this equation down a little bit. If I just simplify that, that turns out to be, so that turns out to be this right here, and I just took care of some of these minus signs and just made it a little bit cleaner. So our dx value is negative 130, our dy is 400, and our dz is 160. Now, how do we find d? Well, d is just going to be the root sum square of all three of these distances. So in other words, it's going to be, d is going to be dx squared plus dy squared plus dz squared, all square rooted. And if we just plug in the values of dx, dy, and dz, we get a value of d to be 450. So that is our value for d. That is the absolute distance from point A, which is right here, all the way to point B. Okay, awesome. So that pretty much gives us our lambda value for AB. So if I just erase this d right here and I replace that with 450, this right here, this entire expression is lambda for TAB. Now this is good because using this equation up here, we can multiply the scalar quantity of f times this lambda value to get the full expression for TAB. So in other words, this tension of AB is going to be equal to the scalar quantity of TAB. And remember, we said that TAB and TAC are equal in tension. This is the same tension in both cables. And I just wrote the quantity there to be just simply T. So I could say that TAB is going to be equal to T times our unit vector lambda, which we found right here. And so this equation turns out to be T times lambda, which is this right here. And if I expand this out even more, this turns into this expression right here. So I just distributed this t value for all these different terms, and that gave us our x component, our y component, and our z component. Now you'll notice that t is still unknown. We don't actually have a value for t, but that's okay. We can leave this in this equation, and once we start figuring out some of the other components in the other force, we can use those equations of equilibrium, this f of x, f of y, and f of z is equal to 0, to figure out these unknowns t, and then that will eventually help us figure out what p and q are. So let's continue on with this example. We have an expression for TAB. Let's do the same thing for TAC. Now for TAC, we're going to do the same thing where we need to figure out what our lambda is for TAC. So in this case, TAC starts at point A and it ends at point C. And so the vector that we're going to look at is going to be the same vector along the line of action for tension of AC. And so our starting point is going to be A, and our ending point is going to be C because the vector is oriented in this direction. So we're going to be looking at these two coordinates, A and C. C is our ending, A is our starting. So we're always going to take the starting value minus the end, start minus end, start minus end, and that will give us our values for dx, dy, and dz. Okay, so if I scroll back down here, I could say that dx has a value of negative 150 minus 0. dy has a value of 0 minus negative 400. And dz has a value of negative 240 minus 0. And again, I'm just getting these values from our original problem statement right here. You have negative 150 minus 0, 0 minus negative 400, and then negative 240 minus 0. That is this right here. So if we solve each one of these out, we get values of dx is equal to negative 150, dy is equal to positive 400, and then dz is equal to negative 240. Now, if we take the root sum square of these three components, we get a value of d is equal to 490. And so now if I expand out, or I write out TAC is equal to, well, the scalar quantity is just T, right? It's the same tension times this unit vector. And I should really label these unit vectors. This is lambda for AC, and this up here was lambda for AB, just so you know that they are different. But anyway, what we can do now is rewrite this by saying T times our lambda value, which is negative 150 in the I, and again, that's coming from dx, and then you have a positive 400j, and then minus 240k, all over d, which is 490, and if I expand this out, I get something like this, where we have this x component, the y component, and the z component for this TAC force. Now, why did I keep things in this sort of a format? Well, I could have easily just divided 150 over 490 and gotten a decimal point, but I think it's just easier to keep it as fractions for now until we start getting into more of the mathematical stuff. So now that we have our force components for TAC and TAB, we can now use our equations of equilibrium right here to figure out what some of these unknowns are. Now, you could start with either the x direction, the y direction, or the z direction first, but looking at this diagram, we can see that p is the only unknown in the x direction, q is the only unknown in the z direction, but for the y directions, there's actually two components, the component for TAB in the y direction and the component for TAC in the y direction, both directly pointing up. Now that's good because we also have one exact force going in the y direction in the opposite sense. It's this weight value. So instead of starting with x first, I'm actually going to start with y, the y direction, and you'll see why in a second here. But what I'll do here is I'll say the sum of all the forces in the y direction are equal to 0. Well, what are the forces in the y direction? Well, if you look at this diagram, we have this weight that's going downwards. So there's going to be a negative 376 Newton force going down. And then we have the y components for TAB and TAC. Now the y component for TAB is this value right here. So we're going to have to add that to our equation, just like that. Okay, so that takes care of TAB. Now what about TAC? Well, TAC has a y component here, 400 over 490 times the tension force. So I can go ahead and write that here as well, just like this. Now, those are the only forces and the force components in the y direction. So I can set this equal to 0 because, again, everything has to be in equilibrium. The forces have to cancel out in all three directions. And you can see here that in this entire equation, I only have one unknown, which is this t variable here. So if we simply do some algebra and we solve for t, we get a tension force of about 220.5 newtons. Now, this is really good because we can take this value and now we can plug it in for all the t value in each one of these components for this TAC force as well as our TAB force. So just by starting off with the y direction, we figured out really 6 different components in this entire problem, which is awesome. Okay, so now what do we want to do? Well, now that we know t, we know the force components in the x direction and the z direction for both of these tension forces, AB and AC. And we can use that information to now figure out what this P force is and what this Q force is. Now, again, you'll notice that P only has a component in the x direction, this PI. And so when we're summing our forces in the x direction, our only unknown is just going to be P in the x direction. So let's go ahead and sum those forces in the x direction and see what we get. So I can say sum of forces in the x direction is equal to 0. And that P force was going positive. So we have a positive P. And then for tension of AB, our x component was this negative t of 130 over 450. So we'll have to include that down here by saying negative t times 130 over 450. And then for tension of AC, our x component was this value right here. It's negative t times 150 over 490. So negative t times 150 over 490. And those are the only force and force components in the x direction. Now, we already know what t is, right? It's this 220.5 newtons. So the only unknown in this equation is p. Now, if we just simply solve for p, we get p has a value of 131.2 newtons. Okay, awesome. So that takes care of, I guess, part A of this problem, which was figuring out one of these unknown forces. Now let's apply that same method in the z direction to figure out what this Q force is. So again, just by looking at this diagram, you can see that Q is the only unknown force in the z direction. And so we can sum the forces in the z direction just like we did for x and y, and that would equal 0. And we could see that for force Q, it is going in the positive z direction. So that value is going to start off with a positive Q, and then we'll need the z components of TAB and TAC. So for TAB, the z component is this value right here. So we can put that down here by saying that's a plus tension times 160 over 450. And then the z component for TAC is this component right here. Now you'll notice here it's actually negative, so be very careful with the signs. In this case, it's not going to be plus, it's going to be minus tension times 240 over 490. And this, of course, is going to equal 0. Now again, we know what tension is. It's 220, so we know this and we know this. The only unknown is Q. And if we just solve for Q, our Q value is about 29.6 newtons. There we go. Our force P has a x component of 131, and force Q has a z component of 29.6.